I'm going to use this example problem to illustrate optical ray diagrams. I'll go ahead and pause and read the question. There are two lenses. The first lens is converging, the second lens is diverging, and they're separated by 400 millimeters. Dimensions and refractive index are given for each lens rather than the focal length, even though they're thin lenses. It's common practice in optical design to not start with focal length or lens power, so the radii of curvature, both front and back surface, and the index of refraction of the glass are what you start with, because those become variables. We'll calculate the resulting focal length of the lenses, and then we will proceed with an optical ray diagram, and then we'll solve this with ray tracing, which is a different thing. The first objective is to find the focal length of the lenses, which is the inverse of the power of the lenses. And to find the power of the lenses, we need to find the power of each surface. Altogether, there are 4 surfaces in this problem. First, find the power of the first surface. Power is the difference in the refractive indices between the two sides of the surface, divided by the radius of curvature of the surface in the paraxial limit. Given an index of refraction of the glass and the radius of curvature of the glass, we have the power of the first surface. The power of the second surface is found the same way, but the glass now is first, and then the air is next. So using n equals 1 for air and n equals 1.517 for glass, n prime refers to the index after the interface, n refers to the index before the interface. The radius of curvature is also opposite in sign for surface 2 because it's concave. The radius is negative. If the surface were convex, then the radius is positive per our sign convention. From this we can get the power of the thin lens. The focal length of lens number 1 is 1 over the sum of the powers, and we get 120 millimeters. If it's not a thin lens, you have to then account for the thickness T of the lens. But in the thin lens limit, the thickness goes to 0, and that's why we can just add the powers. Surface 3's power can be computed by the same approach. Now notice the radius of curvature is negative because it's concave, and surface 4 gives the same power, same sign, and then you add those together as well to get the net power, and the inverse of that is the focal length. So the focal length of lens 2 is minus 80 millimeters. So let's take those computed focal lengths, put them back in the diagram, put x's on the optic axis where those focal points reside. The object, we're told, is 240 millimeters to the left of the converging lens, and it has a height of 2 millimeters. We're taking ourselves in the paraxial limit. So we'll get the same result, including magnification, regardless of what we choose for object height. It's common in optical ray diagrams to have a different scale for the vertical and the horizontal. So let's draw some rays. If a ray comes from the tip of the object, parallel to the optic axis, it will go through the focal point of the converging lens after the lens. A ray that is always easy to draw is a chief ray because it goes right through the dead center of a thin lens. If it's a thick lens, it's more complicated. You drive the chief ray through the vertex of the front surface in that case. But for a thin lens, everything happens at the vertical dashed line, the principal plane. I won't bother drawing the focal ray, but you can imagine what it does. It goes from the tip of the object through the focal point, hits the lens, and emerges parallel. All of those 3 of those principal rays will converge at an image. It's a real image because it's formed from real light, and it's inverted. That real image from lens 1 becomes the object for lens 2. So let's draw some rays from this new object through lens number 2. I'm going to draw part of a ray here. It proceeds parallel to the optic axis until it hits the principal plane of lens 2. And then it goes off at some angle. It is in fact a diverging lens, so that is what it should do. At what angle does this ray proceed after the lens? To find it, you backtrack that ray to the focal point. This is in fact a parallel ray, so it comes in parallel and then it needs to proceed to the focal point. Well, it can't proceed to this focal point. That would be a converging lens. It has to proceed to this focal point as a virtual ray, the dashed line, and then the real light diverges outward. You can always draw a chief ray that goes from the tip of the object to the dead center of the thin lens. And now we have 2 rays, the parallel ray and the chief ray. Where they intersect, you have a new image. And that's the final image then of the system. It's inverted and it's virtual. You know it's virtual because it's not formed from real light. This is a virtual part of the parallel ray that is being used to locate it. Now I have the benefit of doing this on a computer, and I can take advantage of some of the very precise measuring techniques that are available with sketching in PowerPoint. So I measured this to be 54 millimeters, where everything is scaled. So if the distance between these two lenses is 400, this distance right here comes out to 54 millimeters in that scaling. It has a size with the same scaling as the object. When I measured the length of this blue arrow, I got 0.667, 2/3 of a millimeter. From that we have a magnification. It's the height of the image divided by the height of the object. And we have a magnification then of minus 0.333, negative because it's inverted. Less than 1 meaning it's small. That's the solution by optical ray diagram.